Hello, welcome back. So today we're gonna talk a bit about uh, the chemical accounting. So we're in chapter 5, dealing with chemical accounting, and here we go. Here are the learning objectives. Hopefully this will be a shorter show for you, but we shall see. Depends on how much I talk, I suppose. So chemical equations, and this is chemical accounting. And maybe you feel this way already, but you might feel like, man, I could really use a translator for this class. And actually, there's books that treat chemistry like it's a different language. Like chemistry is a second language, so we do have a lot of vocabulary, and there's a lot of weird ways of looking at things. And so also in everyday life, like when you look up a recipe, like recipe how to make pancakes, you usually get to like one egg and then this much volume of milk, this much volume of flour, and then instructions, and then the kind of thing. That's what you're kind of used to. And we do have formulas for certain products. So you look at formulas for like soap, and even more importantly, you have recipes on how to make them and these kind of things. And but then you have the chemists that looks at things at the atomic level, and we do things differently. So chemistry is it doesn't make sense in that regards to normal day life. So we have to, as a chemist, as a good chemist, as I guess I'm not a teacher too, I have to translate this to you and how you do this in everyday life. So let me explain to you my craft using everyday language. So first of all, chemical equations. There are a lot of information in these equations, and they represent things. So let's look at this equation here. 2 H2s plus O2s makes 2 H2Os. So the 2 in front of the H2, that means there's 2 hydrogens, and the hydrogens, that's H2. That the H2 is 2 hydrogen atoms hanging out together. So there's 2 H2s, and say there's 4 hydrogen atoms there. And then you add oxygen there, so the O2, that means that you have 2 oxygen atoms with that oxygen, and not include these are all going to be gases. So we have 2 hydrogens and 1 oxygen as the reactants. They're on the left side of the equation, and we form 2 waters, so 2 H2Os. And there's 2 waters, and each of them have 2 hydrogens and 1 oxygen. And notice, though, that on the left side of the equation, there are 4 hydrogens. The right side of the equation, there are 4 hydrogens. Left side of the equation, there are, 2 oxygens. And then the right side of the equation is 2 oxygens. So this is known as a balanced chemical equation. So it tells you the number and what is reacted, and then the product. Just like a recipe for making pancakes, except we are using atoms instead of things like eggs and flour and milk. Okay, so reactants are on the left side, products are on the right, and the arrow means yields, reactions produce, that kind of thing. So the arrow, and depending on the reactions, some reactions are one way, some can go either way. But like for instance, with if you're making pancakes, you can't go from pancakes back to flour, milk, and eggs, but you can go flour, milk, and eggs to form pancakes. So some reactions can go forward and backward, some reactions cannot. It just depends. Okay, and in the chemical equations, we have the states. So S in parentheses, this means solid, L means liquid, G means gas, and AQ means aqueous, and I've heard aqueous too. So aqueous means it's dissolved in water. And lots of things are dissolved in water here on Earth, including many of our solutions in our body, for instance. Okay, so we've mentioned here that hydrogen plus oxygen makes water, and a couple of no-nos you cannot do. You cannot change, so if you look here, so sin number 1, changing the chemical equation. So hydrogen plus oxygen makes water plus an oxygen radical. That is properly balanced, but now you've introduced a new product, and maybe you don't really want oxygen radicals. Maybe you do. Maybe that's a good thing to have, but as written, we do not want that. The other thing is, you can't just start adding, like, oh, how do I get rid of this thing? Like, well, I was making a new molecule. So H2O is a different molecule than H2O2. One is water, one is hydrogen peroxide, right? So this breaks, calling this would break the, although that's a properly uh, written equation, both of them are, but this is the law of multiple proportions. So you can have two elements and form different compounds but in different ratios. We're wanting to make the ratio of water as in 2 parts hydrogen to 1 part oxygen atom-wise. So how do you balance this? You have to make sure that there's the same number of same number of atoms of each type on each side of the chemical equation, as written there in the on part C. Okay, and chemical equations with volumes, the law of combining volumes, this is good old Avogadro figured this out, or at least he hypothesized originally. So ammonia is 3 hydrogens plus nitrogen makes 2 ammonias. And this is part of the gases. And Avogadro is the one. You can see here that ammonia is NH3. They look kind of like those little jellyfish things on the right. But you have hydrogens here, and 3 parts hydrogen, 1 part nitrogen to form 2 ammonias. And here is Avogadro, like, woo, man, he looks like Mr. Burns in The Simpsons or something. I would not be happy with this representation myself. I'm sorry, Avogadro, we did not do a good job drawing you in this book. But Avogadro's number is well, you've already mentioned this before, it's defined by 12 grams of carbon-12, and it has that many atoms. And this number could change soon in the future, as we might switch to silicon. We mentioned that with the kilogram as well. Okay, the mole is defined by Avogadro's number. And we mentioned this before, that a mole, we have this huge number to describe atoms and molecules that tend to be very, very tiny. So the idea here is to give you an idea how big Avogadro's number is. So if we have a baseball, and if you have a mole of baseballs, that's about the same as the mass of the Earth. And if you have a mole of raindrops, that's about the mass of the ocean. So that's gives you an idea how big Avogadro's number is. So I'm a very hard man to buy. I'll tell you what, if you give me a mole of dollars, I will gladly give you an A in this class. Of course, that's ridiculous because there's not that much money right now. So I'll even accept a mole of pennies. Of course, a mole of pennies would probably be the mass of like Mars or something. But sure. All right, now you know my price. So use it wisely. Okay, formula mass. So this is the also known as molecular mass or atomic masses. So it's the amount, the mass of something that equals 1 mole. So if you want to know the molecular mass of water, for instance, or how do I figure out if I have a mole of water? 18 grams of water, that's a molecular mass equals a mole. So if you have 18 grams of water, that is a mole of water. And then by that, you know the number. You know that's 6.02 times 10 to the 23rd molecules of water. And here are some examples of a mole of things. So sugar there, that's 342 grams as a mole of that. Salt, that's 58 grams. Carbon, that's 12 grams. Copper, I think that's 65. I don't have a periodic table in front of me. It's about 65 grams. And then helium there's, well, assuming it's at 0 degrees, that's 22.4 liters. I don't know what it would be in other temperatures. It would be slightly larger for room temperature. But that illustrates a mole of each of these things. And that means, although you can see that the size varies, the volume varies, the masses vary, but the things that they have in common is that there are a mole of each of these things shown here. And I mentioned this, the standard temperature and pressure is 22.4 liters, and we define this at 1 atmosphere of pressure and a temperature of 0 degrees Celsius. So higher temperature is going to have a higher volume, higher pressure is going to have a lower volume of gas. Okay, and mole and mass relationship in chemical equations, we have a whole field called stoichiometry. Stoichiometry deals with the chemical accounting in this. And the coefficients, so the numbers that come before the different molecules in a chemical reaction, um, they represent moles. They could represent individual atoms, but for most part, we use moles because most of the chemistry we do is large scale. You can do single atom, and we do some single atom spectroscopy, but that's a very small field that does this. So let's look at this equation here, and I've already mentioned this equation before. Two hydrogens, or two moles of hydrogen gas react with 1 mole of oxygen gas. I know it's not written to form 2 moles of water. Or you could say yield or combines to form or however you want to describe it. And how do you write the stoichiometric calculation? Balance the chemical reaction. It's very important. Write and balance it. Determine the molecular weight or molar masses of the substances involved in the calculation. And then use these coefficients to get the right amount of something. So meaning like how many shoes do I need to have? And there's a 2 shoe to 1 person ratio. Well, there's also different types of shoes. Maybe a ham sandwich would be better. How do I make a ham sandwich? Well, I need 2 pieces of bread and 1 slice of ham. So a ham sandwich, a mole of ham sandwiches would require 2 moles of bread slices and 1 mole of sliced ham. That kind of stuff. And then use the molar mass to convert the desired amount to how much you need. So this is important for if you are working as a chemist and need to figure out the recipe and how much to make stuff for stuff. Okay, and this is an illustration of the previous slide. If you like this better, this is a how-to to get from one species to another in terms of mass. Okay, solutions. Actually, before I go on this slide, let me tell you a little bit about where this stuff is useful. I used to work at a company called Ecolab. If you go to the bathroom, like at school, if you're at a school or anything public, and they have like a soap dispenser, the soap is probably made in Ecolab. And I was an intern for a manufacturing plant in Ohio, and I hated that job, actually. I'm glad I don't work in manufacturing, but different people love it. So if you like manufacturing, kudos to you. We really need you to help us with our work and to make soaps. So thank you for your help with that. But I personally did not enjoy the job. Anyways, when you made the soaps, there was these people called mixers, and they'd have these huge tanks where they would make the soaps, and there was a recipe. It'd tell you things like, put 10,000 gallons of water, put 2 drums of isopropyl alcohol, put a drum of sulfuric acid, put 3 bags of sodium hydroxide in here, put 5 pounds of blue dye number 4 in there, and like it gave orders to things, and that people working in the mixing tanks, they typically had a high school education at best, and then they would make the stuff, and then it would send the product. Well, it would go through the quality control lab to make sure each step was fine, and it would be sent along the filling stations to fill. But behind all those mixing instructions was research. It was the chemist and various other people, of course. The chemists would break things down atom-wise, and then after they broke things down atom by atom, they would have to scale it up to a usable form that the mixers that are not chemists, that are just not just, but high school, they're not chemists, I should say. They don't have training in chemistry. Need to be able to mix those things and make them properly. So there was a lot of communication going on there. The other thing, so to note, the mixers, they got exposed to a lot of chemicals. So, I mean, using straight lye, and they're tearing bags open with knives and pouring lye as sodium hydroxide. It's very dangerous. And, I mean, I've seen them get hit by live powder, and you can get burns. You get burns from that stuff. So, uh, and the point is that a lot of jobs have a huge amount of chemical exposure to them, and believe it or not, chemists is a very safe profession. Chemists rarely get occupational illnesses. I mean, we do, of course we do, but we are much more cognizant of what we're doing. Tend to be, depends on the chemist, of course, but we're much more aware of what we're doing, and also know how to remedy and when to be hyper about things, when not to be. I took an art class at UH Manoa, and it was interesting looking at the artists. Some of the things they were afraid of, and some things they weren't. They probably thought I was weird. I wore a gas mask when I was grinding metal, for instance, and I always had safety glasses on, so that's okay. I survived and didn't get anything in my eyes. But okay, the point is, what I'm trying to say is that the chemists, we do have a language, and the language is important. But we also need to be able to communicate to other people. It needs to be relatable. Otherwise, the knowledge of chemistry, it will just stick with us, and then nothing will be made useful out of it. And so I'm trying to help teach you understand some of the chemistry language. So that's part of my job. Okay, so moving on, talk about solutions. A solution, definition of solution, is a homogeneous mixture. So if you remember mixtures, homogeneous mixtures are also known as solutions. And depending on how much stuff is in something, it's a concentration. So like if you ever look at ingredient lists and formulas, it'll say things like made from concentrate. Your cranberry juice is made from concentrate. Well, what does that mean? You can go to the grocery store. I remember it's the orange juice, right? You can buy the little tube of orange juice in the frozen juice section, and you can dilute it in a pitcher to form orange juice. And what is that plug of really strong orange juice goodness called? It's called orange juice concentrate. You have the orange juice goodness in a really small volume. So concentration means amount per volume. If there's a lot of stuff in a small amount of volume, that's known as concentrated. And if there is very little stuff in a very large volume, that's known as diluted. So you can dilute solutions that way. Oh, and solvent, I should go back. Solvent means what is dissolving, and solute is what is dissolved. So solvents, the most common solvent, of course, is water. A lot of times when I say solvent, they refer to hydrocarbons. Like, this is a solvent-free mixture. It's just means you have water instead of alcohol or gasoline or something like that. Okay. All right, molarity, chemistry, right? We're the weird people. We use the concentration unit molarity. And the amount per volume, it's number of moles per liter. So amount per volume, and designated by the capital letter M. And we can also do other types of concentration. You can do percent by volume. Volume of solute, what is dissolved, divided by the volume of solution. And percent by volume is used very largely is in alcoholic beverages. So the word proof means twice the percent by volume. So 40 or 80 proof whiskey is actually 40% alcohol. So it's double the volume of the solution. Percent by mass, the amount of whatever divided by the total mass times 100. So this is done for things like anything about body fat percentages. If you're 20% body fat, that means you have 20 parts body fat per 100 parts person. So same idea, you can have something by percent by mass. Although we use molarity mostly in chemistry class. Not in class, but in the world. For instance, though, hydrochloric acid, the way you make concentrated hydrochloric acid, it's 38% mass hydrochloric acid per in water solution. This is the saturated. That means you can't get any more in. This is also a concentration of about 18 molar. If you want to know the concentration, this is about 18 molar. But the way this is made is hydrochloric acid is bubbled through uh, water until it no more will be absorbed, and that ends up being 38%. And green chemistry here. So again, why are we doing this? What is the point of this class? For the point of this class, besides getting your diversification in physical science and learning about chemistry, of course, because chemistry is awesome, and also because chemistry is essential science, and we it leaks over to many other classes. The future for us, though, and challenges is our world and our diminishing resources, and also the effects that we have on the environment, trying to limit those. So we want to try and limit the atom economy. So meaning we want to reduce the amount of fossil fuels we burn to get the products. We want to reduce the amount of ore that we need to get our personal products like cars and whatnot, and computer screens. So ever this is what we're looking towards, is to improve our efficiency, to improve the economy, the atom economy, I should say, because of this. And now we are done. Okay. Hopefully this was a little less arduous for you. Only 20 minutes.